This is the first of the videos in our new topic, which is probability. And in this first video, we'll be giving you some introduction to key terminology, axioms, and definitions we'll use in terms of probability. So this will be the scope of the next couple of weeks. And in particular, in terms of the data science life cycle, it's really going to be the connecting theory that gets us from EDA to being able to predict and infer information about, say, a population. So that's really where probability and probability distributions come into play. And in general, those are going to be key things that we use when we're trying to model data that we get or model scenarios that we observe in the world. So I think based on all of our experience with coins and or dice, you may have some preconceived or at least some basic thoughts in your mind about what I mean by probability. And so I'm going to start with an example. If I were to say, suppose you roll a fair six-sided die just once, and I ask you, what's the probability you roll a multiple of 3? Think for a minute what comes to mind as to how you may or may not answer this. And I'm going to leave you hanging here, but I just wanted to put it in the context of something that you may have already seen. We'll come back to how mathematicians are going to define this, but for now, just give it your best guess. Okay, so we're going to now define some terms, and then we'll come back to what we mean by probability, in particular for this example. So we're going to define some key terms used in probability, and the first is the idea of a set. So a set is just a collection of unordered objects. The objects are called elements or members. And frequently you'll see us use these curly brackets and then the actual elements listed inside of them, and that's called roster notation for a set. Now, I want to point out that sets can have repeated elements in it. That's fine. But when you are thinking in the context of a set, I want to ask a question. Do you think this set A is considered equal to the set B? In terms of how we think of sets and our definition, yes, it is considered equal. And that's because we're just going to look at distinct elements and see if they have the same distinct elements. In this case, they each have the distinct elements 1, 2, 3, so they are considered equal sets. One other term we'll be using is the idea of what's called a subset. And so that's, in a good example here, if we consider the set of all polygons, then a subset of that would be this set of regular polygons, right? So it's a subset if all elements of one are also elements of the other. One other piece of notation that I wanted to point out is what we use for what's called the empty set. So you'll either see the roster notation with nothing inside, or you'll see this null value, and we'll see these come up. Okay, now let's put this in the context of probability. So for probability ideas, we're going to have some commonly used terms. The first is we're going to talk about experiments. And in the context of probability, an experiment is something that can be repeated. It has to involve some element of chance, and it's going to have well-defined outcomes. So that rolling of the die is a perfect example of an experiment. There's the element of chance, because I don't know what number is going to land on the upward face of the die, but I do know the possible outcomes. The outcomes are the result. So in the case of rolling the die, I have a set of possible outcomes that are either 1, 2, 3, 4, 5, or 6. And that set is what we call the sample space. Then we're going to talk about the size of a sample space. And so that's referred to in math terminology as the cardinality of a set. We'll use these bar notation, almost looks like absolute values here, but that's a way of us denoting in shorthand the number of elements in a given set. And then finally, we're going to define events as a subset. Any subset of S can be considered an event. So let's make this more concrete. We started with that fair six-sided die, And so our sample space using roster notation is just going to be the set of integers, values that I could get from rolling the die, which means the cardinality of that, or this notation, is just 6. There's 6 possible outcomes. And then a specific event, rolling a multiple of 3, we can write that in terms of set notation. I'm either getting a 3 or a 6. And so you can see this event here is a subset of the sample space. Same idea, but now let's do it with flipping a fair coin twice. So now I'm going to denote the sample space in terms of the outcomes. I'll just say H for heads. So I could get heads and then heads. I could get heads and then tails. I could get tails and then heads, or tails and tails. In this case, I have 4 elements in this sample space. There's only 4 possibilities. And then I can think of the subset of getting at least one tail that either looks like tails, heads, heads, tails, or tails, tails. So that's my event, E here, and I'm just denoting it as a subset. All right, let's talk about a couple other key set notation ideas. And the first is when we talk about the union of 2 sets, or in our case, the union of 2 events, E and F. Suppose that my experiment is I'm rolling a die, so we know my sample space. Let E be the event that I roll a 1 or a 2. F is the event I roll a 2 or a 3. So if I want the union, this is going to contain all outcomes in E or F, which is why I'm now writing that as 1, 2, 3. Similarly, we can define what's called the intersection of events. And so in this situation, the intersection, and I'm going to make a caveat, in our class, we'll be using this intersection notation, or we will also be using this E comma F. And that notation will come into play when we actually do probabilities. So here in this case, the one that's in both is just the number 2. And we're also going to define what are called mutually exclusive events. And that means that there are no shared elements in the set. So we say that the intersection is the empty set. And then we're going to talk about the complement of a set. And so what we mean by this is the event that contains all outcomes that are not in your original set. So if I want the complement of rolling a 1 or a 2, I'm going to take everything else in my sample space that's not a 1 or 2. And that will be the complement set. You're going to often see we'll use the notation either the set to a C, or we'll use this E and then just a prime. That's another type of notation that's consistent or often used when talking about complements. And then we're going to end this quick crash course in set theory with 2 important laws that are really useful when trying to look at how both intersections and unions and complements kind of all interact. So the idea is, first, if I wanted to visualize the intersection of A and B, and I'm thinking of A as, this, I didn't even put any elements in here, but just imagine I have elements in here, I have elements in here. So B are going to be whatever elements are in both. A intersection B will be whatever elements are in both. If I want the complement of that, that's going to be all the green area, or any elements in the green area in this picture. That is the same as actually taking A complement or B complement. So you can convince yourself this with a picture, but if I take A complement, it's going to be everything outside of A, like that, all the way outside. And then I'm going to have or everything outside of B, which will then help me get the rest of this, right? It also includes all of this, everything outside of B, but I want either or, and that's how I end up shading in the entire green region. And then similarly, we can use it to look at the complement of a union. So if I have A or B here, which is everything inside both circles, and then I take the complement, that's everything in green. And notice another way I could have gotten that was by taking everything outside of A. So everything, A complement is everything outside of A. And again, this visualization, when I'm saying everything outside, I'm including any elements that are not in A. And then I want an and everything that's not in B. And so when I do that, I want to get both of those. That's going to end up giving me just the green area that's shaded. So practice or shade that yourself if you're trying to visualize that a little more. But that's a useful connection between unions, intersections, and complements. So now let's talk about what we actually mean when we say probability. And I wish I could say, oh, there's one clear defined definition of probability and here it is. But actually it gets more philosophical than that. Especially when we start talking about events like what's the probability of an earthquake next year? What's the probability that the CU football team makes it to a bowl game? These are things where it's not so cut and dry. It's not like rolling a die or flipping a coin. And so when you have situations that are not super clear like this, there's actually two different lines of thought as to how people go about assigning probabilities. The first line of thought is frequently called the objective or frequentist interpretation, and it conceptualizes probabilities as relative frequencies. So what would occur in the long run if you repeated an experiment over and over? And that is considered the probability. So, for example, here's the notation, but let's write this out. Let's say I want to come up with the probability of some event occurring. I'm going to perform n trials of some experiment, which could result in that particular event occurring. And then I'm going to define the probability of the event occurring as the ratio of the number of trials that actually resulted in that event. That's what I'm writing up there as count event, divided by the total number of trials. And that limit notation, that lim as n goes to infinity, is notation from calculus. It's the idea that if I continue doing this over and over and over for larger and larger, more and more experiments, at the end of the day, there's going to be some number that this ratio is approaching or converging to. And that's what we're going to define as the actual probability. So that's one way of defining probability, and it's actually the way we will be using in this class. But I want to point out that that definition is tricky when there are things that you want probabilities for where you don't have a long-term experiment that you could simulate or data that you could get from the past to actually, give you an estimate. And so in scenarios where this frequentist interpretation breaks down, some people have argued that you could think of probability instead as more of a subjective degree of belief. And there's a whole interesting theory called the Bayesian probability theory and Bayesian statistics that is based off of this way of thinking of probabilities. For just one reference, I'll give you a basic example on the next slide. Suppose that your insurance company says, well, a new driver has a 20% probability of getting in at least one accident during their first year, so that's why your premium is higher, right? So they cite some probability that they're using to create their insurance premiums. Depending on which view you're thinking of, the frequentist view can really be like this. Maybe this is based on past data. Maybe they have a lot of data of new drivers, and they look at, all right, how many of those new drivers actually end up in an accident during their first year, and they see that in general that number is right around 20%. You can define the probability that way. But it's also possible to think of it in terms of, well, maybe I have created a model. Maybe the people who constructed the insurance model, for whatever reason, they brought in other info that they have, maybe not just the number of occurrences, but other information. And they believe with 20% confidence, a new driver will get in an accident during the first year. That's more of a Bayesian interpretation. Still valid, but it's bringing in some subjective degree of belief into the calculation. Regardless of which of those schools of thought we're looking at, there are some three main axioms, think of them as starting points, for defining a probability function that we all agree on. So these are basic truths for playing the game of probability. The first rule is that probabilities must be numbers between 0 and 1. Okay. The second rule is that all of the outcomes must be from the sample space. So the probability of the entire sample space is equal to 1. And the last one is saying if you have two mutually exclusive events, then the probability of one or the other is the sum of the probabilities. So again, in our notation, I could use this union notation as well. And this just gives us a nice starting point for which we can start to calculate probabilities of more interesting scenarios. There's also a follow-up that comes from these. So based on these axioms, you can prove the identity that if you want the probability of a complement of an event, it's 1 minus the probability of the event. And again, that's based on the fact that probabilities have to add up to 1, and you can directly get it from those there. I'm going to just point out that axiom 3 can be generalized even more if you have more than just two mutually exclusive events. This is just notation for saying that I have a lot, the probability of the union of a bunch of them. So here, 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 and it actually even lets me go up to an infinite number. Don't worry about that so much in this class. I'll just stop it there. But the math behind it works even if you want to do an infinite number of events, that it's still going to be the sum of the probabilities of each of the individual events. So those are the rules that we play by when defining probabilities. And in the next video, we're going to look back at that question I asked you about the dice, because that fits in a category of what are called equally likely outcomes. And fortunately, when you have equally likely outcomes, both frequentists and Bayesians agree on how we define probability. And so we'll look at that in the next video.